So good afternoon, everybody. Let me begin by thanking the organizers for inviting me to this very nice venue. It's a pleasure to be here. So indeed, I'd like to talk about perturbative QCD at precision frontier. And with regards to that, I'd basically like to do three things. One is sort of explain where the precision frontier is. What are the kinds of calculations that can be done? But I figured that if I just start listing, this can be done, this can be done, this can be done, it will turn into botany, which might be a bit boring. So I also want to give a bit of an insight into how these calculations are done. So what are the methods that are being used? And I want to touch a little bit on the measurement of the only free parameter of QCD, really the strong coupling. So let me begin straight away. And well, how could I not begin by noting that QCD is celebrating its 50th birthday? So I think the generally accepted paper where QCD was formulated as a non-abelian gauge theory of color is this paper by Fritsch, Gellman, and Leutwiler from '73. And in the same year already asymptotic freedom was discovered, which made it clear that this theory can actually then be used to make predictions, at least at high energies. And it took until the end of that decade to actually get strong confirmation of the theory from events such as this, where we're essentially seeing a hard gluon emission from a QQ bar pair. So QCD is 50. That's a bit old. Why are we still interested, right? Well, to answer that, I think there is an intrinsic interest, and I will try to point out some things of what I mean by that. But ultimately, the reason we're interested is because as particle physicists, we'd like to answer the great questions of particle physics, right? What is dark matter? What is dark energy? How does baryogenesis happen? Where does flavor come from? What about neutrinos? Why are they so light? And so on and so on. So really, what is beyond the standard model, right? What comes next? What is beyond our current knowledge? And well, as we search for answers, we have to acknowledge that currently we're in a situation where the LHC has not yet delivered direct signals of BSM physics. We're all hoping that it will. But this being the case, what we can do is focus on possible small deviations. Sometimes small deviations hide large conceptual issues. Like if you look at the orbit of the Earth, it looks pretty circular, but it's actually not. And there's a big conceptual difference there. So anyway, my point is that the first signs of new physics may well be indirect, and precision is going to be the key. So just to underscore that, let me show you a plot from this publication, which is a projection of exclusion limits for a certain 2 Higgs doublet model at the high luminosity LHC. And what I'd like to draw your attention to is that these models typically predict new elementary scalar particles, which you can then look for. And you can look for them in a direct way, right? Try to produce them, or in indirect ways, for example, by looking at the coupling of the known already observed Higgs boson and looking for deviations from the standard model values. Now, what this plot shows very nicely is that these two ways of approaching the problem are complementary. So the blue regions are exclusion limits from a direct search, while this hashed region is actually the exclusion limit from these precision measurements. And so you see a nice complementarity. And well, we don't know. I mean, if the model is realized over here, we're going to see it in precision physics and not by directly producing the new particle. So what sort of precision are we talking about here? Well, in this same review, it is projected that the high luminosity LHC will be able to deliver sort of 2 to 4%. This is 2%, that's 4% also here. So this kind of reach for Higgs production cross-sections, and these are Higgs couplings to other particles. Now, very importantly, these projections actually assume a substantial, meaning a factor of 2 to 3, improvement of our current theoretical uncertainties. And even so, if you look at these values in particular, which is the Higgs coupling strength to the glue on the top and the bottom quark, they are still going to be theory dominated. So this is sort of the accuracy that we are aiming for. This is the precision frontier, 1% essentially. So how are we doing, and what do we need to do? Well, over here, you're seeing the current uncertainty budget for Higgs production in gluon fusion as a function of energy, so the LHC is sitting somewhere over here. And what I'd like to highlight is that, well, there are a couple of entries here. So you get uncertainty. These PDFs are essentially related to uncertainty with respect to our knowledge of the proton structure as embodied in parton distribution functions, which are essentially just probabilities of finding a parton inside the hadron, inside the proton with a given momentum fraction. Then there are uncertainties, the scale and the EV you see here and here. These are related to our ability to calculate in QCD perturbation theory, which I'll talk about in detail. And then there are uncertainties here which are related to the modeling of quark masses. So what does that mean? Well, that means that if we can, we try to neglect masses because it's easier to calculate. For the B and C, this is, depending on how accurate you want to be, could be a good approximation. And in the top case, of course, setting MT to 0 is not viable at the LHC, but maybe setting it to infinity is, and that's sometimes a surprisingly good approximation. But anyway, you can do an expansion at least in 1 over MT. And so that's what these uncertainties are hiding. And, well, you see that each of them contributes, 1%, 2% to end up at this 8–10% where we are currently. And so, of course, the job of theory is to decrease all of this. How do we do that? Well, I mean, just to point out, sort of to reiterate this information, a parton-parton or a proton-proton collision is actually a pretty complicated thing at the LHC. So there are many aspects of precision that you can talk about. First of all, as I've said, the proton is essentially modeled as a beam of partons, right? So you need to know the composition of the proton precisely in terms of partons. Then you need, then the incoming partons collide, and there's a primary hard scattering. You need to be able to describe this precisely. Then the partons going out will emit additional radiation and shower. This is also, this is called the parton shower part of this process, kind of the red part here. And you want to do as well as you can describing that. And, finally, these partons have to turn into hadrons. The heavy hadrons have to decay. All of this is on top of multiple particle interactions, underlying events. So it's a complicated environment. And refinements can be made in all aspects. Now, in this talk, I would mostly like to concentrate on fixed-order perturbation theory. It's sort of the inner part here. And, well, the usual disclaimer of these review talks is that, of course, the selection is based on personal biases and reflects what I think I know best. So, apologies to many other topics that would deserve their own talk. But I ultimately decided to talk about something that I actually know, so I hope you don't mind that too much. All right, so as I've said, one important aspect of precision is performing higher order calculations in QCD. Now, what does that mean? Well, the tool that we use to make predictions is called perturbation theory, and what this actually means is just that the quantity we are looking for, some generic cross-section in this case, we're going to express that as a power series of some small parameter, while the small parameter is going to be the strength of the interaction. And this whole approach is made viable by asymptotic freedom, of course, which tells us that as we increase the interaction energy, the strength of the interaction as measured by this coupling alpha S actually goes down, and it goes down in a predictable way. And so at high energies, this should be a reasonable approximation. Now, what does this numerically look like at LHC? Well, this strong coupling is roughly 0.1 at the energies that we are talking about, which means that the first contribution, which we call the leading order contribution, is some number, okay? The next to leading order piece, which is the first correction, should then be 10%-ish, right? If this is 1.1 in front, That's kind of the naive expectation. The next to leading order should be around 1%, and then next to is kind of a tongue twister, so let's just call this MQ below. That should be sub% by this naive counting. Now, just a word of warning that the naive counting can be completely off, and I will show you an example of this later. Now, one more thing that I would like to point out here is this dependence on this scale mu that you see in this formula. What is this? Well, this mu comes about because of the need to renormalize the theory in the ultraviolet. So this is sort of a fake parameter. It's not really in the theory. The prediction actually would be independent of this mu if I were able to keep all terms in this series. Of course, I'm not. That would mean that I can exactly solve QCD, which unfortunately we cannot. And so as we truncate this series, a residual dependence remains. Now, you might think that that's a bad thing because then I don't get a precise prediction. I get something depending on what I choose mu to be. But actually, the opposite is true, because what this mu dependence allows me to do is sort of gauge the size of the terms that I'm leaving out, right? Because if everything was included, there would be no mu dependence. So the size of the mu dependence has to tell me something about the terms that should cancel this dependence. Okay, so it's actually a way to assess the impact of missing higher orders. And we will see examples of this in the plot coming up. Okay, so imagine now I want to do the calculation. What are the ingredients? Well, first, so let's, in this simple example, let's do something like I have 2 quarks coming in and I want 2 quarks going out. So, of course, the simplest case is they just scatter, right, interact through a gluon, and you get this little picture, the leading order picture. And this is all fine. That's your leading order result. You compute it, you get a number. Great. Now, what does it mean to go to higher orders? Well, it essentially means that you start adding extra radiation. And this extra radiation can both be virtual or real. What I mean is that extra radiation just means I emit a new particle, right? And this can be sort of reabsorbed inside the process itself, leading to these loop diagrams, right? There are loops in here. Or it can actually be a real radiation, which, however, is unresolved. So what I mean is that if I'm looking at this quark-quark to quark-quark scattering, in the detector, in the end, I'm looking at 2 jets, right? That's what I'm detecting. Now, if I emit an extra gluon, but this is either soft, or, for example, its momentum is collinear to one of the quarks, I still see just 2 jets. So I'm going to clump also this contribution in my 2-jet measurement, okay? So I need to also include it in my theory calculation. So we can add loops and we can add legs, okay? And going to higher orders kind of means, including the terms in this diagram like diagonal by diagonal, let's say. Now, what's the issue here? Well, it's not really that we get more diagrams, although that's not nice either, but okay, we could deal with that. The real issue is that there are singularities sitting inside all of these except the leading order term. And there are 2 types of singularities, and Karel mentioned these already. The UV singularity is removed by renormalization, and infrared singularities, which are a bit more devious because they are actually only removed in appropriate sums of contributions. And I will show that just on the next slide. So if I actually want to implement a QCD calculation, I need to worry about 2 things. First of all, I actually need to compute all the ingredients that you see here. Okay? And, well, there is a well-defined mathematical formula for what these things correspond to. That's not the problem. But this formula, if you have loops, includes some integrals. And I will have more to say on that in a second. So that's one issue, multi-loop integrals. And the other issue is that in this way of representing the result, what you actually have is that the bracketed objects themselves, these sums, are finite, but the separate pieces are not. And that's a problem, because I cannot tell my computer to just compute the 3 things and add them up, because I'm adding 3 infinities, and that could be whatever, right? So, and these infinities come from infrared divergences, so I need some sort of treatment of the infrared stuff to be able to make a an actual computation which yields an actual and correct number. Okay? Now, coming to what is the frontier and what is already known, well, at leading order everything is easy because this is just fine by itself. There are usually no loops, so life is happy. At next to leading order, you typically have one loop integrals and some infrared singularities. However, all of the complications associated with this at this particular level have been well known and essentially solved completely during the 90s, early 2000s. So in fact, at NLO today, the frontier is something like a 2 to 8 process, which is actually quite incredible. So you can compute proton-proton going to top antitop, bottom antibottom, with then both of the tops decaying to a W and a B, and the W further decaying leptonically. Okay, so in the final state, you actually have 8 particles. And this is sort of the leading order process, so you have to add one loop on top of this and one extra emission, and that's your NLO, and this can be done these days. So the level of understanding is certainly there. We have efficient ways of computing the one loop stuff. We have efficient ways of treating the infrared poles by essentially moving contributions around between these two pieces to make them both finite, okay? And then we can proceed to compute them separately once this rearrangement was done. So where are the frontiers? Well, at the next order, beyond NLO, we already start hitting our frontiers. In fact, for 2 loop amplitudes, anything with 4 legs and several masses inside, and I will show an example of this, is already very hard. 2 loops and 5 legs is something where the first results, first complete results have appeared 2 or 3 weeks ago, something like that. So it's absolutely frontier material. 3 loops can be done in very special cases, and beyond is like in our dreams, okay? So this is where the multi-loop amplitudes stand. What about IR pole treatment? Well, for NNLO, I will show you that there are ways to deal with the infrared poles. For the moment, they're really inefficient, so there's certainly things to do there. At N-cube-LO, only very special cases can be treated. The generic problem is understood. The generic solutions, I think, are still quite far away. But this is the direction we are pushing. Okay, so just a few words then on how actually multi-loop computation, what are the methods that go into these computations. And so the first thing I want to touch on briefly is multi-loop integrals. And the first question is, well, why are these hard? And so my answer to that is, well, multi-loop integrals are hard because they're integrals, right? And integrals are generically hard. What that means, right, is that it's not too complicated to write a multidimensional integral that's not solvable, right? So what we have typically is, even for this very simple one-loop case, the thing that you actually should evaluate at the very end is already non-elementary. It's not super difficult in this case, but it's certainly non-elementary. So you very quickly, as you go beyond one loop, run into high-dimensional, very difficult to compute integrals. And you have to worry about divergences, which is sort of a problem in itself. Now, so what is an idea here? Well, an idea here is that instead of actually looking at the direct integral, let's look at the differential equation that is satisfied by the solution. And that might catch you as a really stupid idea. I mean, in analysis class, we do the opposite, right? Solving a differential equation means coming up with an integral that is the function that we're looking for, right? So what am I doing? Well, what you're actually doing is that it turns out that the structure of this differential equation actually encodes more information on the function in a certain sense than the original integral representation. And that's perhaps not too hard to see. I mean, take a simple integral, just do a complicated integral transformation to hide that simplicity, and already you have a complicated integral, right? So this representation is somehow more systematic in a sense than when you're dealing with just a direct integral. Now, I should say that setting up this differential equation is actually algorithmic. However, efficiently running these algorithms is another question, and it's actually the topic of a very active area of research. But in principle, it's algorithmic and can be done. All right, now I should say that this is not a new method. It was thought of essentially in the early 90s and applied successfully to many important processes. But what is new is that we've gained some new understanding, both analytically and numerically, of how to deal with these things. And we also had some new ideas on how to set initial conditions, which is of course, a must if you actually want to get a number out of a differential equation. So just kind of quickly, what happened on the analytic front is that it was understood, more or less, that the structure of the solution in many, many known cases is something called an iterated integral, which in its simplest incarnation is just this thing. I mean, this G is defined by this integral. Take some A's, you know, do these integrals. That's your definition of a G. Many cases, in many cases, it happens that the functions that pop up in these calculations can be expressed in terms of these G's. These are called multiple polylogarithms, by the way. And sort of enough is known about them at this point that you can comfortably use them for calculation. You can also evaluate them numerically, which is not bad. And what I mean by knowing enough to work comfortably is the following. So these 18 pages that you see over here is the result of a seminal calculation of this so-called two-loop hexagon remainder function. And well, these guys computed it, and that's what they got. Okay? And then these mathematicians came along and said, oh, wait a minute, we know something about the functions that you use to write this down. Let us have a crack at simplifying it. And that's actually the result, those two lines. Okay? And the reason I actually included the whole half page is to show you that this is not cheating. So everything that is here is actually explicitly defined on this page. Okay, so that result is actually that result. And that's what I mean by knowing enough about a function space to work comfortably with it, right? If you can do these things, then you can actually use it. So that's one thing that has happened in the past decade. Another thing which is happening sort of right now is that people are realizing that not everything can be expressed in terms of these multiple polylogarithms that I've shown you, but you actually need more generic cases of these iterated integrals, where these functions over here are not just 1 over y minus a, but something more general. Now, the reason I didn't write what they are is because it's really non-trivial what they are. And this is sort of an interesting surprise, and this is one aspect which I think is like intrinsically interesting in studying QCD, that you're getting your hands on like what a perturbative field theory looks like, okay, in general. We're starting to understand the space of solutions in some sense, okay? And what I mean by these being far from trivial is that these are objects related to certain geometric constructions that stem from the differential equation, strangely enough. In some cases, these are elliptic curves, which leads to this notion of elliptic multiple polylogarithms, which is nice, but currently much less is known about them than the normal version of just multiple polylogs. Also, not even their efficient and numeric evaluation is solved completely. However, this really is an area where you know, mathematics and physics meet, and there is progress, there is quick progress, and so I think this might carry the potential for a real breakthrough in the next years, where we understand this class of solutions a lot better. Okay, now let me say just a few words about another point of view of this whole issue, which is that, well, after all, when I'm trying to get a cross-section, a number to compare to experiment, what I really need is a number out of my differential equation, right? As nice as all the math behind it is, I want a number. So can't I just numerically solve the differential equation? And the answer is, well, yes, but you have to be careful because the solution is typically complicated. It will have poles, it will have logarithmic singularities, it will have cuts, so on, so on. And so if you just do a naive approach, the best case is that you get something that's numerically unstable. The worst case is that you just get something that's outright wrong, okay? So you have to understand what you're doing, and one thing that has happened in the past couple of years is that methods were actually constructed to get the correct solutions at very high numerical precision. So, like, imagine you know the function value at some point f0 and would like to calculate it at f of x. Well, you know, naively, just integrate along the orange path. You have the differential equation to do that. Great. Well, yes, except there's a cut here, you're hitting a pole there. So the first thing to do is you have to find a clever path around all of these. And then you have to guarantee that your numerics is stable all the way. And one way to do that is this so-called method of generalized power series, where you're actually writing an ansatz for the solution along each line segment separately, plugging into the differential equation and solving for these coefficients. And the point is that depending on, you can always refine the numerical accuracy by making a bigger ansatz, right? So in principle, you can go to arbitrary precision. And the nice thing is that all of this can actually be automated. So there are codes these days where you can plug in your system of differential equations and it will find the correct paths and do all this for you. All right, last thing on this differential equations business is the question of initial conditions. Right? For a differential equation, you need an initial condition to get a number. And so what was the traditional approach? Well, the traditional approach was you sort of looked for a point where some simplification happened to the original integral and you could actually solve it. And that's nice, but you need to find such a point, and you still need to solve the integral. It's definitely a case-by-case situation. Now, what has happened, again, in the last just couple of years, is that it was realized that you can set up a procedure called auxiliary mass flow, where you have one parameter which in a certain limit, so the idea is you introduce a new parameter into the game, which again seems a bit stupid. I mean, don't we have enough? Why are we introducing one more? Well, the idea is that it can be shown that in a particular limit of this parameter, the integrals always simplify that you have to compute. And that's not all. What is actually the main result is that if in this limit your integral is still not simple enough for you to calculate it, just iterate the procedure. And the end of this iteration is something where you have to integrate 1 over 0 to 1, basically. And that integral even I can do. So that can be done. And so essentially it turned out that any initial condition calculation can be reduced in this way to essentially a trivial problem. So I think that's a really nice result and makes this case-by-case study unnecessary. Okay, let me skip the way how this is done in practice, unless you're very interested at the very end. So these are some of the new developments of the past couple of years that I think have really helped push the field and make possible some calculations which certainly weren't possible before. And so let me briefly speak or give you, some recent precision highlights, let's say. And here, first, let me begin by processes that include massive quarks. And so the new developments here are that we are able to account for quark masses exactly in more and more processes. So here's sort of a list. Let me not read this slide for you. Let me just concentrate on this second to last point here, which is Higgs plus jet production at just NLO with exact top and bottom quark masses. And so I told you that NLO is simple, so what am I talking about? Well, what I'm talking about is the following. If you actually look at this process, it turns out that even at leading order, if you take the top quark mass exactly, you already have a loop diagram, because the Higgs, this dashed line is supposed to be the Higgs, doesn't directly couple to quarks and gluons, right? You need a top quark loop to couple them. So the leading order is already one loop, and then next to leading order looks something like this, right? And inside this diagram there is sitting the Higgs mass, the quark mass, 2 kinematic invariants because this is a 2-to-2 process. And so you have 4 scales, 2 loops, and 4 legs. And that is a cutting-edge problem. In fact, it cannot be solved at this point analytically, even with these new fancy tools. Maybe they have a solution in terms of these elliptic polylogs that we don't know yet. But they can be, these generalized power series methods can be used to give a numeric evaluation. And you see one particular example of like the real and imaginary part of one integral that shows up in here. And these surfaces are actually good numerically to 10 to the minus 25. So that's what I mean by you can get pretty good numerical precision. And then you can use all this to build a phenomenology. And this is just showing a particular plot from this paper of the Higgs PT. So the upshot here is that loop-induced processes with many scales are very challenging even at NLO. However, like this calculation would actually not have been possible without these numerical techniques that were worked out in the past couple of years. There's just no way. All right, next, let me jump to JET. So JETs are, of course, we know, essential analysis tools at LHC. They are used, for example, for the extraction of PDFs, alpha-S. They are a large standard model background to BSM searches, and so on. They're also measured quite precisely over a wide rapidity range and up to something like 5 TeV now. Now, the best that we can do here is proton-protons to 2 or 3 jets at next to leading order. And very recently, the 3-loop amplitudes for 2-parton to 2-parton scattering have appeared, which will actually enter the 2 jets calculation at 1 order higher once we figure out how to do this calculation, actually. Because the infrared problem here is rearing its head. So the amplitudes are known, but you don't know how to combine them into an actual cross-section. Okay, so now one thing I should say is that the 3-jet calculation in particular is enormously expensive. So the CPU time used was like 1 million CPU hours. And 1 million hours is more than 100 years. So that's a hardcore calculation and you need a big computer. But you can ask, well, it's nice to have all these ends, but do you really need it? And the answer is actually you do. If you look at Atlas data for this particular quantity called transverse energy correlation, which was used actually to measure alpha-S. What I'd just like to point out without going into any of the details is that what you see here is NLO theory, and the green bands are theory uncertainty. And the measurements are, well, nicely sitting inside, but the measurement errors are actually way below. So this means that you get some determination, but it's highly inaccurate because your theory is not accurate enough, okay? So the point is, yes, you need this 3 jets at NNLO is very important, for example, to be able to make a correct or a decent analysis out of this set of data. So this is needed. Here you just see some plots for this paper. What I want to point out is that, well, waiting 100 years on your computer is not very good. Probably there are refinements to be made there, right? So maybe you only have to wait a decade. The other thing with these plots that I just want to show quickly is you see the LO, NLO, and NNLO in green, blue, and red. And two things that are sort of generic features is that the leading order description kind of gives an order of magnitude, but it's sort of off. Where the first place where you see like a nice stabilization of the perturbative prediction is from NLO to NNLO, which are kind of on top of each other. The second thing is that the bands that you see come from this variation of scales that I explained at the beginning. And you see, particularly from NLO to NNLO, a nice reduction in that width. Okay, so you have a better control, of course, over uncalculated higher orders because you just calculated a new order. Okay. Last thing I want to mention is that we have begun producing the first results at N³ LO for simple standard candle processes such as gluon fusion to Higgs or Drell-Yan production of W and Z bosons. These calculations for the moment are mostly for total cross sections though, okay? This is another distinction, that computing a total cross section is of course a bit simpler than going to a differential cross section. Nevertheless, some recent highlights are actually the first computation of a differential cross section at this order, as well as total cross sections at n^LO for associated W Higgs and Z Higgs production. Now, just pulling a plot from the fully differential Higgs boson computation, again, what you see is the nice stabilization of the perturbative prediction going from NLO to NNLO to n^LO, the shrinking of the scale variation band, and one more thing that I alluded to at the beginning is, look, leading order is this gray band that's not even really visible. Now, if you look at the numbers, well, the next to leading order correction is like more than 100%, right? So your naive expectation of, well, 10%, 1%, 0.1%, in this case is completely off, okay? So in fact, I mean, the first real prediction is NLO, really. The leading order is, well, okay, it's sort of getting the shape right, and like the order of magnitude is okay, but that's it. All right. So those were, I think, some of the tools that we use and some of the recent highlights in terms of calculations. And in the last couple of minutes, I want to talk a little bit about measurements of the strong coupling. So the strong coupling, of course, is a fundamental parameter of the standard model. And I mean, it's just a constant of nature. So for that reason alone, we'd like to know its value precisely. But, you know, on a more practical level, its numerical value enters essentially every prediction we make at LHC. So we have to know it, and we have to know it precisely. The way we obtain it is, of course, from fitting theory to measured data. And, well, this looks back on a rich history, so there are many different approaches and many different observables and categories of observables even that you can use to measure this, from low energies such as tau decays, which you see up here, the results from tau decay measurements, up to like LHC, which is a TeV and beyond these days. Okay. Now, in the following, I would just like to flash two results of measurements, and my main point would be to highlight the role that higher order corrections that I've discussed before are playing in bringing down the uncertainty of these measurements. So the first example, which I actually had something to do with, is the measurement of alpha S in energy-energy correlation in electron-positron annihilation. Now, energy-energy correlation is something that was proposed to measure before we even knew the gluon was there. So it's one of like the oldest observables people thought of to measure in electron-positron annihilation. It's essentially just the energy-weighted distribution of angles in an event. So you look at all the particles, they go out in different directions, right? And you construct this energy-weighted distribution. Now, since you know this is an old idea, it's actually been measured quite extensively at LEP and before. And the theory available is pretty precise. There's NNLO theory at fixed order, and also NNLL resummation next to leading log, which I will explain in a second. So this means there are lots of measurements, good theory, so there's a potential for a precision extraction of alpha S. Now, what does this actually look like? Well, of course, you need some data. Those are like the black dots. And then you need to work out your theory predictions. So here you see what the fixed order predictions look like. Again, notice that the description of data becomes better and better as you move to higher and higher orders, although it's far from perfect, even at NNLO, and I will explain a little bit why that is in a second. But one region where it's not really visible on this plot, but the description is really, really bad, is over here, because the data turns around. While you can't really see it, but the prediction shoots off to infinity. So that's completely bad. So there are two choices. Either you do something about the prediction here, or you just say, I'm not going to use this data because the prediction is completely off. Now, why is the prediction completely off? Well, the reason is the following. It actually turns out, if you look into this, that at each perturbative order, your prediction will include a term that looks something like this. So alpha S to the n. and then a logarithm to the 2n minus 1 of a variable y, where this y actually goes to 0 as you're entering this peak region, okay? So what happens is, even if my alpha s is small, eventually as y is going to 0, this logarithm is going to compensate, right? At some point this log has to become 10, and from that point on, I have no business expanding in alpha s anymore, because at each order I'm getting the same term, okay? So what must be done in these cases is that such terms which have this logarithmic behavior need to be systematically resummed to all orders. And what that means is that sort of the structure of your result looks kind of like this. Schematically, of course, and there are functions, regular functions of y multiplying all the terms over here. But what you need to do is fixed order calculations would amount to summing up row by row, right? But if you want to get the behavior correct for small y, you actually have to sum up column by column and do this summing up all the way. So this has to be summed to infinity. And this can be done in certain situations for certain observables. And so you have a leading logarithmic prediction if you include this column, and next to leading logarithmic prediction if you include two columns, next to leading logarithmic prediction, and so on, however many n's you can add. Okay? In this particular case, we can add 2 n's at the time of this measurement. Nowadays, we could add 1 more n to the logarithmic resummation, and that's what it looks like. The point here is that your prediction now actually has a physical behavior, okay? We can discuss how good the description of data is, but at least it's not going off to infinity. All right. But you also see that, of course, this resummed prediction isn't very good even for moderate angles, and that's not its fault. I mean, it's not designed to be good there. It's designed to be good around this peak. So, of course, what you want to do now is you want to say, well, since I actually know exact perturbative corrections, and I also know logarithmic resummation, why don't I package all this information up into one prediction, which then should be good both in the peak region and kind of throughout. And so this is called matching, and I don't want to really go into any detail here. The point is that you want to count, you know, some number of rows and some number of columns in such a way that you don't actually perform any double counting. That's called a matching. Okay, so last thing. Well, why isn't this prediction very good over here? Well, one of the issues is that in the calculation we're using quarks and gluons. Those are partons, right? But in a detector, I'm certainly seeing hadrons. And so those partons somehow have to turn into hadrons, right? Now, this process, of course, is called hadronization, and it's something that cannot be described in perturbation theory, so it must be modeled in some other way. Now, there are generically two ways, either through the use of analytic models or Monte Carlo tools, that we can do this. In this particular case, the Monte Carlo tools were used because it's actually known that the analytic model isn't very well suited to this particular observable, although it's useful in other circumstances. So here you just see some results of these are like post-fit predictions. That's what it looks like for certain data. And when you do the fit, this is what you get out. So your alpha s at next to leading order plus next to leading log looks like this. Now the important point I want to make here is that if you repeat everything with only one change, namely throwing away one n from the fixed order prediction, then you get this result. So this is 0.117 plus minus 0.0028. On the other hand, this is 0.122 plus minus 0.0053. Okay? And the big difference is over here. So this n, one n in the fixed order prediction actually cuts your uncertainty in half. Okay? So that's, I think, a big deal. And this is, in the end, why you do these calculations, because you want to get precise numbers. All right. Now, in the very last couple of minutes, I would like to just present a very recent extraction of alpha s, one more, which is from the LHC this time, where you will see a very dramatic impact again of higher orders. So what was studied is the Drell-Yan process, which is basically the production of charged leptons in PP collisions. And so this is by itself an electroweak process, but the way you measure alpha S is, of course, these incoming quarks can radiate, and once they radiate, the Z boson recoils against this radiation, and the strength of the recoil is proportional to the strength of the strong interaction, and so you get a handle on that strength by looking at the PT distribution of the Z boson. This is actually a very nice process at LHC because it's a clean experimental signature with leptons. Backgrounds are low, and so it can be measured very accurately. And look, the theory is extremely precise. We have n cube LO, even approximate n4 LO nowadays, and we have approximate n4 LL resummation, where approximate means something. It's not the full thing, but whoever made the calculation thinks they've nevertheless got the main piece of the next order correct. It's a good way to add one more n to your calculation. Anyhow, so this of course means that since very precise measurements can be made and very accurate theory is known, you have a potential for a precision measurement. Now here's what the data looks like. What they've actually measured is the double differential cross-section as a function of PT in several rapidity beams. For, in this case, the dilepton mass constrained to be around the Z boson mass, so from 80 to 100 GeV, with some further selection. And here is the theory that is supposed to be describing these measurements. The PT distribution computed this time at all these orders, like leading order isn't even, they have so many n's that leading order isn't shown anymore. Right? We don't care, that's child's play, right? Well, actually, leading order for this observable, I mean, at leading order, the Z boson doesn't have a PT, it's just a Dirac delta function sort of sitting at 0. So these next to leading order is the first case where you get like a non-trivial distribution. So in that sense, it makes a lot of sense to not show leading order. You wouldn't see anything anyway. All right, so here it is. This is the theory that can be used to fit against. Hadronization in this case was handled by an analytic model with some model parameters, which can be varied to assess the uncertainty associated to the modeling. And that's what you get once you do the fit. So these are post-fit ratios. Now, the description is very, very nice, especially for the lower rapidity beams. And also notice that even with all this theory, the theory error is much bigger than the experimental measurement error, but that's how it is. Now, with all of that, you can extract the value of alpha S, and here it is, and this is quite incredible. So they get 0.11828 plus 0.0008 minus 0.0088, okay? And so if you actually know what the world average looks like, this error is smaller than the world average of all the other measurements ever done, basically. So this is the most precise experimental extraction of alpha S, and it's as precise as the current particle data group average. Of course, where does this precision come from? Well, first of all, the clean experimental signature and the high experimental sensitivity, but also the very complete and very thorough theory modeling, where here they're nice enough to actually give us a plot where you can see what happens if you just use, in this case, they listed the logarithmic orders they're using. Next to logarithmic, next to logarithmic, n cube and n4 approximate. And well, I mean, the drastic reduction in the theory uncertainty is very clearly visible. Over here, you essentially see the measurement down here, this measurement, and then the current world average is the purple band. Okay, so that's a very nice new measurement, and well, this is where the frontier is now, at this level of agreement, or at this level of uncertainty. So that brings me to my summary and outlook, and I will be kind of brief. Let me just now flip it around and first recap the alpha S part. So it's of course a fundamental parameter which we'd like to measure precisely. I think, or I've tried to make the point that higher perturbative orders is absolutely crucial to get the theoretical uncertainty under control. And I've shown you the new world record for LHC, which is the most precise alpha-S measurement. And I mean, of course, look for improvements. The keen-eyed may have noticed that this data is actually for 8 TeV. So there's, of course, a bunch of more data at higher energy to analyze as well. Now coming to the more general topics, I hope to have convinced you that precision is key in looking for new physics right now. There are many aspects of precision. Here I focused on higher order calculations in perturbation theory and QCD. With regards to that, the frontiers currently are at NNLO. Many processes are known, but calculational efficiency is an issue. The new, bleeding edge, let's say, is N-cube-LO. It's going to be a great challenge to go beyond that for sure, and even a great challenge to go to somewhat less simple processes at N-cube-LO than what are known. However, many people are at work, and I think we're seeing advances in both analytic and numeric technology that do have the potential for a breakthrough in the next years. All right, and I would just like to finish by again reiterating that, well, the market of uncertainties, let's say, is pretty diverse. Higher orders that I've talked about is just one aspect. You certainly have to consider, PDFs, the description of parton evolution, parton showering. Can we obtain a much more refined understanding of hadronization, and so on. So missing higher orders is an important, but not the only player in the game here, of course. So I would say that we have witnessed great progress in perturbative QCD over the past years, but many questions and many challenges remain, and so that means there are exciting times ahead. And so with that, let me thank you for your attention.